The James Webb Space Telescope launched on Christmas Day, 2021. Within its first year of full operation, it returned images that forced astronomers to revise estimates of how many galaxies exist in the observable universe upward by a factor of 10. Earlier surveys had placed the figure at roughly 200 billion galaxies. Webb's deeper infrared observations pushed that number toward 2 trillion. Not 200 billion, 2 trillion. What that number means, how astronomers arrived at it, and why it changes the way we understand our position in the cosmos, is the subject of this video. Before we dive deeper, if this kind of content genuinely interests you, consider subscribing, because what you're about to see only gets more surprising from here. And I post videos like this every single day. Now, let's continue. We begin with something you can test right now. Step outside on a clear night, away from city lights if you can manage it, and look at the band of faint light stretching across the sky from horizon to horizon. That pale ribbon is our galaxy, the Milky Way, seen from inside. Every individual star you can distinguish with the naked eye is a member of it. The bright ones and the faint ones, the ones that seem to flicker, and the ones that burn with steady cold light. All of them are your neighbors in an astronomical sense. All of them share the same vast rotating disk you also occupy. For most of human history, that ribbon was not just a feature of the night sky. It was the universe, the entirety of it, not the visible part, not the nearby part, the whole thing. Beyond the pale glow overhead lay simply the dark background against which it shone. Nothing more, as far as any human being could know or reasonably suspect. We now know that picture was not just incomplete. It was wrong in a way so foundational that correcting it requires rebuilding the human sense of scale, almost from scratch. The challenge of studying our own galaxy has always been a problem of location. We are inside it. Imagine trying to draw an accurate map of a city while standing in the middle of its most crowded intersection, surrounded by buildings in every direction, unable to step back, unable to gain altitude, unable to see anything but what is immediately around you. You could describe your block, map the adjacent streets, outline the neighborhood, but the full shape of the city, its boundaries and districts, the way its structures connect and flow into one another, would stay hidden. That is precisely the problem astronomers have faced for centuries when trying to understand the Milky Way. Not a failure of intelligence, not a failure of effort, a fundamental constraint of position. Ground-based telescopes helped. Radio astronomy helped further, because radio waves penetrate the thick curtains of interstellar dust that block visible light across wide regions of the galactic disk. Infrared observation extended the reach further still. Scientists mapped large sections of the Milky Way using these techniques, assembling the picture piece by careful piece over decades. They identified the central bar structure, a dense elongated cluster of older stars running through the galaxy's core. They traced spiral arms curling outward from that bar. They calculated rotational velocities, estimated total mass, and modeled the distribution of star-forming regions. The picture improved, slowly, never completely, always with gaps and uncertainties, but it improved. By the early decades of the 21st century, scientific consensus had settled on a galaxy roughly 100,000 light-years in diameter. Some estimates pushed toward 120,000 light-years when the outer disk's full extent was taken into account. Others held closer to 87,000. The precise figure remained contested, but the order of magnitude was clear. The Milky Way was, by any human standard, immense. 1 light-year alone is approximately 5.88 trillion miles. Hold that figure for a moment. Nearly 6 trillion miles, the distance light travels in a single year, moving at 186,000 miles per second, without pause, without slowing, for the entirety of 365 days and nights. Now multiply that by 100,000. The number you arrive at is so far outside the range of anything human beings build or travel that it stops functioning as a number in the usual sense. It becomes something closer to a symbol, a placeholder for a magnitude our minds acknowledge without truly grasping. That figure felt enormous. It was enormous. It still is. Then James Webb launched. The James Webb Space Telescope left Earth on the 25th of December 2021 aboard an Ariane 5 rocket from the Guiana Space Center in French Guiana. It spent the following month executing one of the most complex deployments in the history of spaceflight, unfolding its sun shield, deploying its secondary mirror, unlatching and opening the 18 hexagonal segments of its primary mirror one by one, then drifting to its operational position at the second Lagrange point, a gravitationally stable location roughly 1 million miles from Earth, where the telescope floats in permanent alignment with the Sun. From there, its gold-coated mirrors cool to temperatures near negative 266 degrees Celsius, cold enough to detect the faintest whispers of infrared light. Arriving from the most distant reaches of the observable universe, Webb was not designed primarily to study the Milky Way. Its instruments are optimized for deep field observation, for looking outward across billions of light years at objects whose light has been stretched by cosmic expansion from visible wavelengths into the infrared. Its mission was to see further back in time than any instrument before it, to reach the first galaxies, to observe the universe when it was still an infant. But in doing exactly that, it accidentally, or perhaps inevitably, reframed everything about how we understand our own galaxy's place in the larger picture. In one of Webb's deep field images, the telescope captured thousands of galaxies in a region of sky so small that you could cover it entirely with a single grain of sand held at arm's length from your face. Think carefully about what that means. A grain of sand at arm's length, a speck chosen at random from any direction in the sky, and inside it, thousands of complete independent galactic systems. Each of those galaxies contains anywhere from tens of billions to several trillion stars. Some are spiral-shaped, structured like our own Milky Way with curving arms and central bulges. Others are elliptical, smooth spheroids of ancient stars, the gravitational remnants of galaxies that exhausted their star-forming gas billions of years ago. Others are irregular, their shapes distorted by collisions or gravitational interactions with neighbors. Some appear small and faint, not because they are small in reality, but because they are so fantastically distant that even the collective light of hundreds of billions of stars is compressed into a faint smudge by the time it reaches Webb's mirrors. All of them are real. All of them are complete. All of them are independent island universes. And our galaxy, the Milky Way, is simply one of them. To understand why Webb's images carry the weight they do, you need to understand what came before them and how astronomers learned to measure the cosmos in the first place. The history of that effort is itself one of the most remarkable intellectual journeys in the entire record of human thought. For most of human history, measuring the cosmos meant measuring what you could see, which was the sky as it appeared on any given night, a fixed dome of stars rotating overhead in predictable patterns. The idea that those stars might be distant suns was entertained by a handful of ancient thinkers, but it remained philosophical speculation rather than scientific conclusion. The scale of the universe in any meaningful sense was simply unknown. It was large. How large was a question no one had the tools to answer. The first serious crack in that ignorance came with the development of stellar parallax in the 19th century. The principle is simple. Hold your finger in front of your face and close one eye. Now open that eye and close the other. Your finger appears to jump against the background. That apparent shift in position is parallax, and it arises because your two viewpoints are separated in space. The further away an object is, the smaller the parallax shift. By measuring the angle of that shift precisely, you can calculate the distance. Astronomers applied this principle to nearby stars using Earth's orbit as the baseline. As Earth moves from one side of its orbit to the other over 6 months, the nearest stars appear to shift very slightly against the background of far more distant stars. By measuring that shift, in many cases tiny fractions of an arc-second, astronomers could calculate how far away those nearby stars actually were. What they found was immediately sobering. Even the nearest star to our own Sun, Proxima Centauri, sits at a distance of roughly 4.24 light-years. In human terms, that is approximately 25 trillion miles. Even traveling at the speed of the fastest spacecraft humanity has ever launched, you would need tens of thousands of years to reach it. The stars visible to the naked eye, which feel close enough to name and navigate by, are separated from us by distances that reduce all of human history to a rounding error. Parallax worked well for nearby stars. For more distant ones, the parallax shift was too small to measure accurately with the instruments available. A different technique was needed, and it came from an unexpected source. In the early 20th century, an astronomer named Henrietta Swan Leavitt was working at the Harvard College Observatory, cataloging stars in the photographic plates produced by the observatory's telescopes. She was studying a particular class of stars called Cepheid variables, stars that pulsate in brightness in regular cycles, brightening and dimming over periods ranging from days to months. Leavitt noticed something extraordinary. There was a precise, reliable relationship between how long a Cepheid's pulsation cycle took and how intrinsically luminous the star was. The longer the period, the more luminous the star. This was a discovery of tremendous practical value. If you could observe a Cepheid variable anywhere in the universe, measure how long its pulsation cycle took, and thereby determine how luminous it truly was, you could compare that true luminosity to how bright it appeared in the sky. The difference between those two values would tell you exactly how far away it was. Cepheids became standard candles, objects of known intrinsic brightness, that could be used to measure cosmic distances the way a ruler measures length, Edwin. Hubble used Cepheid variables in the 1920s to demonstrate something that transformed humanity's understanding of its place in the cosmos. He found Cepheids in what were then called spiral nebulae, fuzzy, diffuse patches of light visible through telescopes that many astronomers assumed were relatively nearby clouds of gas within or just outside the Milky Way. When Hubble measured their distances using the Cepheid method, he found they were not nearby at all. They were not part of the Milky Way. They were millions of light years away. They were other galaxies, complete independent systems of stars comparable in scale to the Milky Way itself, separated from it by distances so vast that the light arriving from them had traveled for millions of years before entering his telescope. The universe was not the Milky Way. The Milky Way was one galaxy among many. How many was not yet clear, but the implication was staggering. The observable universe had just grown by an extraordinary factor, and it had done so in a single stroke. And then, a few years later, Hubble made another discovery. He found that the light from distant galaxies was systematically shifted toward the red end of the spectrum, a sign that those galaxies were moving away from us. Not just a few of them, almost all of them. And the further away a galaxy was, the faster it appeared to be receding. The universe was not static, it was expanding. This was the observational foundation of what would become the Big Bang Theory, the understanding that the universe had a beginning, that it began in an extraordinarily hot and dense state, roughly 13.8 billion years ago, and that it has been expanding outward in every direction ever since. The galaxies are not moving through space away from each other in the ordinary sense of motion. Space itself is expanding, carrying the galaxies with it, the way dots drawn on the surface of an inflating balloon move apart, not because they are moving relative to the balloon surface, but because the surface itself is growing. This expansion has a direct consequence for the size of the observable universe. Light travels at a finite speed. 1 light year is the distance light covers in 1 year. The observable universe is, by definition, the sphere of space from which light has had enough time since the Big Bang to reach us. Since the universe is approximately 13.8 billion years old, you might expect the observable universe to extend 13.8 billion light years in every direction. But because the universe has been expanding continuously throughout that time, the actual radius is considerably larger. The galaxy, it is almost certainly not bounded there, but no light from further out has had time to reach us. We cannot see it. We cannot detect it. We cannot, in any operational sense, know what is there, because information traveling at the speed of light from those regions has not yet arrived. The universe we can observe is 93 billion light years across. Our galaxy is 100,000 light years across. Divide one by the other. The Milky Way spans approximately 1/160th% of the observable universe's diameter, and that is in terms of diameter alone. In terms of volume, the ratio is smaller by many more orders of magnitude. In terms of volume, the Milky Way is a single molecule of water in a body of ocean that extends beyond the horizon in every direction. That is where we live. Now let us understand what Webb found when it looked into that ocean. In 1995, astronomers made a decision that many colleagues considered professionally reckless. They pointed the Hubble Space Telescope, the most celebrated scientific instrument on Earth or in orbit at the time, with a waiting list of observation requests stretching years into the future, at a small patch of sky near the handle of the Big Dipper. The patch was chosen specifically because it appeared completely empty. No bright stars, no known galaxies, no visible features of any kind, just darkness. The concern from skeptical colleagues was understandable. Hubble time was extraordinarily valuable. Hundreds of researchers had proposed observations of fascinating known objects, newly discovered supernovae, nearby planetary systems, star-forming nebulae, galaxies in the process of collision. Instead, the telescope was being asked to stare at nothing. It stared for 10 consecutive days. The shutter stayed open while Earth rotated, and the telescope maintained its lock on that small patch of apparent emptiness. When the exposure was complete and the data processed, what came back transformed the field of astronomy permanently. That apparently empty patch of sky was not empty. It contained more than 3,000 galaxies, each one a complete independent system of stars. Each one a self-contained structure of billions of stars, dark matter, gas, planetary systems too small to individually resolve, and history stretching back billions of years. The image became known as the Hubble Deep Field, and it answered one of the most basic questions in astronomy in the most direct possible way. Is the universe mostly full or mostly empty between the galaxies? The answer was full. Staggeringly, incomprehensibly full. But Webb went further. When James Webb turned its instruments toward deep sky, toward similar patches of apparent emptiness probed with its superior infrared sensitivity, it did not simply match the Hubble Deep Field. It dismantled the comparison. Where Hubble could see galaxies to a certain distance, limited by the wavelengths it was designed to detect, Webb could see much further. The expansion of the universe shifts light from distant objects. The further away something is, the faster it recedes, and the more its light is redshifted toward longer wavelengths. Galaxies at truly extreme distances have their light shifted entirely out of the visible spectrum and into the infrared. Hubble, designed primarily for visible and ultraviolet observation, could not see them at all. Webb, with its infrared instruments cooled to temperatures near absolute zero, could see them clearly. What Webb found in its deep fields were galaxies at distances placing them within the first few 100 million years after the Big Bang. The universe is 13.8 billion years old. Webb was detecting objects from when the universe was 300 million years old, 500 million years old, 800 million years old. These were not ancient stars in a nearby galaxy. These were entire galactic systems already formed, already containing billions of stars, already structured into recognizable shapes, existing at a time when the universe was less than 5% of its current age. The light from these objects has been traveling through space for more than 13 billion years. It left its source before our solar system existed, before Earth existed, before the sun ignited, before any of the heavier elements that make up your body had been forged in stellar interiors and scattered by supernovae across the interstellar medium. That light has been crossing the expanding void of space for a span of time that dwarfs everything humans have ever done or built or thought about. And all of this is arriving at Webb's mirrors from a patch of sky you could cover with a grain of sand. The question that followed from these observations was both immediate and deeply unsettling. If one tiny, arbitrarily chosen sliver of apparently empty sky contains thousands of ancient galaxies, how many galaxies exist across the full sphere of the observable universe? Earlier models based on Hubble-era surveys suggested approximately 200 billion galaxies. After Webb's deeper observations and the subsequent modeling work they enabled, researchers began revising that figure dramatically upward. Current estimates suggest the observable universe may contain something in the range of 2 trillion galaxies. 2 trillion. Try for a moment to situate that number in the context of human experience. If you had lived for 2 trillion seconds, you would have been alive for approximately 63,000 years, longer than any anatomically modern human fossil we have found. If you stacked 2 trillion $1 bills flat on top of each other, the pile would extend from Earth past the orbit of Mars. The human brain, with its estimated 86 billion neurons, contains fewer cells than the number of galaxies in the observable universe divided by roughly 23. Each of those 2 trillion galaxies is itself a system of anywhere from millions to trillions of stars. Each of those stars is a sun, a nuclear furnace powered by the fusion of hydrogen, generating light and heat, and in many cases planetary systems. Some small fraction of those planetary systems, orbiting some small fraction of those stars, in some small fraction of those galaxies, almost certainly harbor conditions suitable for chemistry to become complex, for complexity to become life, for life to become something that asks questions. The Milky Way is one entry in that list. Webb did not just reveal how full the universe is, it revealed something else, something that has proven genuinely difficult for cosmological models to absorb. Some of the galaxies it found should not exist, not in the sense that they are merely surprising, but in the sense that the physics as we understood it, the models built carefully over decades to explain how structure forms in an expanding universe, said they could not have formed that quickly or grown that large in the time available. The standard model of cosmological structure formation, called lambda CDM for cold dark matter with a cosmological constant, predicts how galaxies should assemble over time. It begins with tiny quantum fluctuations in the density of the early universe, minute regions that were very slightly denser than their surroundings. Gravity amplified those fluctuations. The denser regions attracted more matter, which made them denser still, which attracted more matter still. Gradually, over hundreds of millions of years, matter clumped into the first stars, and those stars clustered into the first galaxies. The model predicts the distribution of galaxy sizes and masses at different cosmic epochs. Webb's observations have found objects that strain those predictions. Some of the galaxies detected from the earliest cosmic epochs are more massive, more structured, and more star-rich than the model says they should be. They appear to have assembled their stellar populations faster than the available time and the rate of star formation that theory permits should allow. Some researchers have proposed that the initial star formation rate in the very early universe was higher than previously modeled. Others have suggested that the environments in which the first galaxies formed were denser than standard simulations captured. Still others point to possible observational uncertainties. The distances and masses of these objects are inferred from their light, and those inferences involve assumptions that may not hold perfectly at extreme distances and extreme redshifts. The scientific process here is exactly what it should be, a confrontation between new observation and existing theory conducted rigorously and without predetermined conclusions. The model may be adjusted, it may be substantially revised. It may in certain aspects turn out to be correct, and the observations may require reinterpretation. That is how science advances, but what is not in question is the underlying reality that Webb's images reveal. The universe is old in ways that exceed easy comprehension. It has been building structure, stars, galaxies, clusters, and the vast network of interconnected filaments and voids that astronomers call the cosmic web for nearly 13.8 billion years. And in all that time, across all that structure, our galaxy is a relatively modest and relatively recent addition to the inventory. Understanding our place in that inventory requires one more conceptual leap, one that many people never take, because the number involved is simply too large to motivate the effort. It requires understanding not just how many galaxies there are, but how they are organized. Because the universe is not a uniform distribution of galaxies scattered randomly through space. It has structure, it has architecture, and that architecture extends from scales barely larger than individual galaxies all the way up to the largest coherent structures in the observable universe. Structures so enormous that their very existence has forced cosmologists to confront the limits of their models. Galaxies live in groups. Our own galaxy is a member of what astronomers call the local group, a modest collection of approximately 50 to 80 galaxies, depending on how you count the smaller dwarf galaxies orbiting the two dominant members. Those two dominant members are the Milky Way and the Andromeda galaxy. Andromeda is roughly 2.537 million light-years away from us, a number that sounds vast and is vast, and yet on the scale of what comes next, represents an almost intimate proximity. Andromeda is slightly larger than the Milky Way. It contains perhaps 1 trillion stars to our galaxy's estimated 200 to 400 billion. It is a barred spiral as well, oriented at an angle to us that makes it appear somewhat oval rather than face-on. But galaxy surveys have mapped its structure in considerable detail. Andromeda and the Milky Way are gravitationally bound to each other, and in approximately 4.5 billion years, they will collide and merge into a single large elliptical galaxy. That collision, given the vast empty spaces between individual stars within each galaxy, will destroy neither and kill nothing directly, but will dramatically reshape both into something new. The local group, of which both the Milky Way and Andromeda are members, is itself embedded in a larger structure. The local group is a relatively sparse and peripheral member of a larger concentration of galaxies called the Virgo supercluster. The Virgo supercluster spans roughly 110 million light-years and contains dozens of galaxy groups and smaller clusters. At its gravitational center sits the Virgo cluster, a dense knot of approximately 1,300 confirmed galaxies packed into a region roughly 15 million light-years across. But the Virgo supercluster itself is not the largest coherent structure in the neighborhood. It is, in fact, an appendage of something much larger. In 2014, a team of researchers led by R. Brent Tully used a new mapping technique based on galactic velocity flows to delineate the full extent of the supercluster structure in which the Milky Way resides. They traced the boundaries of this structure by following the coherent gravitational motions of galaxies, the way groups and clusters flow toward common centers of mass, the way rivers flow toward the sea. The structure they delineated, they named Laniakea, from the Hawaiian words for immeasurable heaven. Laniakea spans approximately 520 million light-years. It contains approximately 100,000 galaxies, with a combined mass of roughly 100 quadrillion solar masses. It is shaped not like a sphere but like an irregular sprawling structure, with lobes and filaments radiating from a dense central region around, which the component galaxies flow at. Laniakea's apparent gravitational center of influence sits an enormous concentration of mass known as the Great Attractor, a region around which hundreds of thousands of galaxies, including our own, are being drawn at hundreds of kilometers per second. The Great Attractor is not a single object. It is a region of exceptionally high density in the distribution of matter, where dark matter, galaxies, and galaxy clusters are concentrated enough to exert gravitational influence across hundreds of millions of light-years. For decades, its nature was obscured from direct observation by the zone of avoidance, a band around the sky where our own galaxy's disk, with its dense clouds of dust and its billions of foreground stars, blocks our view of what lies beyond. Infrared and X-ray observations have helped penetrate the zone of avoidance partially, revealing the Great Attractor region corresponds to the Norma cluster and a broader structure called the Hydra Centaurus supercluster, and beyond that, to an even larger concentration called the Shapley supercluster. Laniakea is enormous, and yet Laniakea is itself just one supercluster in the cosmic web. The cosmic web is the largest confirmed structure in the observable universe. It is the name given to the network of galaxy filaments, immense threads of dark matter and galaxies stretching across hundreds of millions of light-years that form the skeleton of the universe's large-scale structure. Between the filaments lie enormous voids, regions of space nearly emptied of galaxies, stretching across hundreds of millions of light-years of near-nothingness. At the intersections of multiple filaments sit the densest concentrations of matter, galaxy clusters and superclusters. The whole structure resembles a vast three-dimensional foam or sponge, walls and filaments surrounding vast empty bubbles, connected into a network that extends as far as our instruments can see. The cosmic web emerged from those same primordial density fluctuations that seeded the first galaxies. The slightly denser regions of the early universe attracted matter gravitationally. Matter flowed along the paths of least resistance, accumulating in sheets, then filaments, then nodes. The voids grew emptier as matter was pulled toward the denser regions. The filaments grew denser as they accumulated what flowed down from the surrounding sheets. The nodes grew densest of all. This process took billions of years. Webb observes the cosmic web at multiple epochs. In the nearby universe, it maps the distribution of known galaxies in sharp infrared detail. In the distant universe, it detects the precursors of the web, the protoclusters and early filaments that would, over billions of years, evolve into the structures we observe today. What Webb sees is a universe that was organizing itself into large-scale structure very quickly. Some of the protoclusters detected at high redshifts are already showing signs of the dense, hub-like organization that characterizes mature galaxy clusters in the present day. The seeds of the cosmic web were planted early, and they grew fast. Our position in all of this is worth stating clearly and directly. The Milky Way sits in the outer reaches of the local group, itself a peripheral member of the Virgo supercluster, which is a lobe of Laniakea, which is one supercluster in the cosmic web. We are not at the center of anything. We are not in a particularly dense or dynamically interesting region of the universe. We occupy a quiet rural address in a universe that has far more dramatic neighborhoods of galaxy clusters containing thousands of members, of filaments where new stars ignite by the millions, of nodes where the gravitational energy of quadrillions of solar masses bends space and heats gas to temperatures hotter than the centers of stars. We live in the suburbs of an ordinary galaxy in an ordinary group in a province of the universe that the largest structures would not even notice the absence of. There is one more dimension to the story of the universe's actual size, one that goes beyond mere spatial extent. It involves not just how large the universe is, but how old the light is that Webb catches, and how that age transforms the meaning of everything we observe. When you look at a star, you are not seeing it as it is now. You are seeing it as it was when the light currently entering your eye left its surface. For the Sun, that delay is approximately 8 minutes and 20 seconds. The time light takes to cross the roughly 93 million miles between the Sun's surface and your eye. When you look at the nearest star beyond our Sun, you are seeing it as it was 4.24 years ago. When you look at Andromeda with the naked eye on a clear dark night, that faint smudge just visible without optical aid, you are seeing it as it was 2.537 million years ago, when early humans were first appearing on Earth. The light entering your eye right now was just leaving the Andromeda galaxy at the time our ancestors were learning to use stone tools. Webb looks further. The galaxies in Webb's deepest fields are being observed as they were more than 13 billion years ago. The light arriving at Webb's mirrors from the most distant confirmed objects left those objects when the universe was a few 100 million years old. The universe has aged by more than 13 billion years since that light began its journey. The galaxies that emitted that light have been evolving, merging, growing, changing for all of those 13 billion years. What they look like now, we cannot know by looking at them, because the light showing us their current state will not arrive here for another 13 billion years. The universe is not just spatially vast, it is temporally vast in a way that intertwines with spatial vastness through the finite speed of light to produce something genuinely alien to ordinary experience. In ordinary life, distance and time are separable. You can be far away in space and present in time, or close in space and distant in time. In cosmology, they are coupled. The furthest things we can see are the oldest things we can see. The present state of the furthest objects is forever inaccessible to us. We live in a universe that presents itself to us, filtered through the physics of light travel time. A universe in which looking outward is always simultaneously looking backward, and in which the furthest reaches of space are also the earliest chapters of time. Webb's images are portraits of the universe at multiple ages simultaneously. A single deep field image contains galaxies at dozens of different redshifts, representing dozens of different cosmic epochs, all captured in the same exposure, all arriving at the same mirror at the same moment. Having traveled vastly different distances and vastly different times, it is a document of cosmic history in which the chapters are not arranged sequentially, but all present at once, layered in depth across the sky. There is a question that sits underneath everything Webb has revealed about the universe's size, and it does not get asked as often as it should. Not the question of how large the observable universe is, not the question of how many galaxies it contains. The deeper question is this: what does it mean for the universe to have a size at all? And what lies beyond the boundary of what we can observe? The observable universe is not the universe. It is the portion of the universe from which light has had time, since the Big Bang, to reach us. It is defined not by a physical wall or boundary, not by a region where space ends or changes character, but by a limitation of information. Beyond the edge of the observable universe, the universe almost certainly continues. The current best understanding in cosmology is that the total universe, the full extent of space including everything beyond what we can observe, is vastly larger than the observable sphere. Some estimates, based on the geometry of the observable universe and the degree of spatial flatness our measurements indicate, suggest the total universe could be at least 23 trillion light-years in diameter. Other models, particularly those arising from inflationary cosmology, suggest it could be effectively infinite. We cannot confirm those estimates. We cannot observe beyond the observable universe by definition. We cannot send a signal there and wait for a reply. That region is, in the most complete sense, outside our causal horizon, not hidden behind an obstacle that better technology might someday overcome, but genuinely unreachable, separated from us by a distance so enormous that even light traveling since the beginning of time has not bridged it. And that boundary is not static, it is moving away from us. The universe is expanding, and at sufficient distances, the expansion is fast enough that the space between us and the most distant objects is growing faster than the speed of light. This is not a violation of special relativity. The objects themselves are not moving through space at superluminal speeds. Space itself is expanding, and there is no relativistic speed limit on the expansion of space itself. The result is that there is a sphere of space, called the Hubble sphere, within which objects are receding from us slower than the speed of light, and beyond which they are receding faster. Objects beyond the Hubble sphere that are currently emitting light toward us can still be observed because their light is in a region of space that is still catching up to us, even as those objects themselves continue to recede. But objects beyond the cosmological event horizon, the furthest distance from which light emitted right now will ever be able to reach us, are permanently beyond our observational reach. Their light emitted today will never arrive here. The expansion of space will carry them away faster than the light can close the gap. The universe is not just large, it is actively becoming more inaccessible. Every second that passes, a small additional shell of the universe crosses the event horizon and enters the region from which no further information will ever reach us. The observable universe is, in this sense, shrinking, not in physical size, but in terms of the fraction of total reality it represents. The number of galaxies we can ever observe is finite, and it is decreasing. James Webb, operating right now in this cosmological moment, is catching light from objects that our distant descendants may never be able to see at all. In billions of years, the expansion of the universe will have carried the most distant galaxies across the event horizon permanently. The night sky of the far future will contain fewer observable galaxies than the night sky of today, not because those galaxies will have ceased to exist, but because the light they emit will no longer be able to reach the region of space where any future observers might be located. Future astronomers in the very distant future might look at the sky and see a universe that appears to contain only a local cluster of galaxies, unaware that beyond the horizon lies a cosmos of 2 trillion galactic systems, receding in permanent silence. Webb is operating in a privileged cosmological window, a moment in the universe's history when enough time has passed for the first galaxies to have formed and aged, and for their light to reach us, but not so much time that cosmic expansion has hidden them forever. It is a window that will not remain open indefinitely. Let us turn now from the boundaries of the observable universe to the structures within it, and specifically to what those structures are actually made of. Because the cosmic web, for all its extraordinary complexity, is not made primarily of what we can see. It is made primarily of something we cannot. Dark matter is not a hypothesis. It is an observational conclusion arrived at through multiple independent lines of evidence that collectively leave no reasonable alternative. Dark matter does not emit, absorb, or reflect electromagnetic radiation of any kind. It does not shine. It does not block light. It does not interact with normal matter through the electromagnetic force. It interacts only through gravity, and its gravitational effects on the visible matter in the universe, the stars, the gas, the dust, the galaxies are unmistakable, consistent, and pervasive. The original evidence came from galaxy rotation curves. When astronomers measured how fast stars at different distances from the center of a galaxy were orbiting, they found something unexpected. In a galaxy containing only the visible matter we can detect, the stars at the outer edges should orbit more slowly than stars closer to the center, just as the outer planets of our solar system orbit the sun more slowly than the inner ones. Instead, the orbital velocities of stars in the outer parts of galaxies are roughly constant, or even slightly increasing, all the way to the galaxy's visible edge. The only explanation consistent with the observed rotation curves is that the galaxies are embedded in large halos of unseen mass, dark matter that extends well beyond the visible disk and provides additional gravitational force to the outer stars. This is not a small correction. The dark matter halo of a galaxy like the Milky Way is estimated to be substantially more massive than the visible matter, the stars, the gas, the dust in the galaxy's disk. The Milky Way's dark matter halo extends perhaps 10 times further than its visible disk, to distances of hundreds of thousands of light years from the galactic center. Our galaxy, in terms of total mass, is predominantly dark. The glowing spiral of stars that we call the Milky Way is, in a very real sense, a luminous trace of a much larger and more massive invisible structure. The most direct evidence of dark matter's separability from ordinary matter came from observations of galaxy cluster collisions. When 2 galaxy clusters pass through each other, the ordinary matter in the clusters, the hot gas that pervades the intracluster medium, is slowed by electromagnetic interactions and pressure forces as it collides with the gas from the other cluster. Dark matter, interacting only gravitationally and not electromagnetically, passes through essentially unimpeded. Gravitational lensing maps of colliding clusters have shown the dark matter halos separating from the ordinary matter during the collision, confirming both that dark matter exists as a distinct component and that it behaves exactly as predicted. Webb contributes to dark matter research in important ways. By observing galaxy clusters and measuring how they distort the light of more distant background galaxies through gravitational lensing, Webb can map the distribution of mass, including dark matter, in those clusters with unprecedented precision. The degree to which a cluster bends and distorts background light depends on its total mass, including the dark matter, not just the visible matter. Webb's sharp infrared vision makes it exceptionally good at detecting and measuring these gravitational lensing distortions. The results confirm and refine what previous observations established. Dark matter is real. It dominates the mass budget of galaxies and clusters. It forms the scaffolding along which the visible structures of the universe are assembled. The cosmic web is, at its deepest level, a dark matter web, a network of dark matter filaments within which the luminous galaxies are embedded, like beads on invisible threads. Alongside dark matter sits an even more mysterious component: dark energy. Current best estimates attribute approximately 68% of the universe's total energy density to dark energy, approximately 27% to dark matter, and approximately 5% to ordinary matter, the atoms that make up stars, planets, gas clouds, and human beings. Everything we can see, touch, measure directly, or build instruments to detect constitutes roughly 1 part in 20 of the universe's total content. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. In 1998, 2 independent teams of astronomers studying distant supernovae found that the universe's expansion is not slowing down as expected. Early cosmological models assumed that gravity would be gradually decelerating the expansion initiated by the Big Bang. Instead, the supernova data showed that the expansion was speeding up. The most distant supernovae were dimmer than they should be if the universe were decelerating, meaning they were further away than expected, meaning the universe had expanded more than predicted. The only way to explain this was to invoke some form of energy permeating space uniformly, an energy that does not dilute as the universe expands, but maintains a constant density as space grows. This energy exerts a kind of pressure that acts opposite to gravity, not pulling matter together, but pushing space apart. Whether the cosmological constant truly captures the nature of dark energy, or whether dark energy is something more complex, a dynamic field that changes over time, remains one of the most active areas of theoretical cosmology. Webb contributes to dark energy research through its precise measurements of distances to galaxies at various redshifts, helping refine the expansion history of the universe and constraining the parameters of dark energy models. Webb has also brought renewed attention to a tension in cosmology that has proved stubborn and increasingly significant. The tension concerns the Hubble constant, the value describing the current rate of the universe's expansion. The Hubble constant tells you how fast a galaxy is receding from us for every unit of distance it is away. It is one of the most fundamental parameters of the standard cosmological model, and 2 different methods of measuring it give answers that disagree with each other by more than the uncertainties should allow. The first method uses observations of the cosmic microwave background, the faint glow of thermal radiation left over from the early universe when it was hot and dense enough to be opaque. About 380,000 years after the Big Bang, fitting. The standard cosmological model to those observations gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method uses the cosmic distance ladder, a chain of distance measuring techniques starting with parallax for nearby stars, extending to Tethid variables for nearby galaxies, and using type Ia supernovae as standard candles for more distant galaxies. This method gives a Hubble constant of approximately 73 kilometers per second per megaparsec. The discrepancy is about 9%. That sounds small, but in a mature field where measurement uncertainties are carefully quantified and systematically reduced, a 9% gap between 2 independent measurements of a fundamental constant is deeply significant. It has persisted despite extensive efforts to find systematic errors in either measurement chain, and it has actually grown more significant in statistical terms as both methods have been refined to higher precision. Webb directly engaged with the Hubble tension. One of the original hopes for Webb was that it could refine Cepheid distance measurements sufficiently to either confirm or reduce the discrepancy. Webb, with its superior infrared capabilities and spatial resolution, observed the same Cepheids that the Hubble Space Telescope had measured, but with greater clarity and less contamination from nearby stars in crowded galactic fields. Webb's Cepheid observations confirmed the Hubble Space Telescope's results to high precision. The distance ladder result held up. The tension with the microwave background-derived value remained. If anything, Webb's confirmation of the distance ladder measurements strengthened the case that the tension is real, that it reflects a genuine inconsistency in the standard cosmological model rather than a measurement artifact. What could explain the Hubble tension? The possibilities range from modest to revolutionary. At the modest end, there may be effects in the early universe, subtle changes to the physics of the recombination era that slightly alter the predicted Hubble constant without requiring dramatic revisions to the overall model. At the more revolutionary end, the tension might be pointing toward new physics entirely, modifications to general relativity at cosmological scales, or exotic forms of dark energy that evolve over time in ways not captured by the cosmological constant. The scientific community has not converged on an answer. The tension remains active, unresolved, and consequential. Webb also illuminates the universe through gravitational lensing with a richness no previous instrument could match. The phenomenon occurs when a massive object, a galaxy cluster, a concentration of dark matter, sits between us and a more distant source of light. The mass of the intervening object bends the path of the light passing near it, exactly as Einstein's general theory of relativity predicts. The result is that the background source appears distorted, stretched, magnified, or multiplied in the image we observe. For strong gravitational lensing, the effect is dramatic. Background galaxies are stretched into arcs and rings, or even replicated into multiple images by the concentrated mass of a foreground cluster. Webb images of galaxy clusters routinely show dozens of these lensing arcs, thin curved streaks of light that are actually distant background galaxies, their images distorted by the cluster's gravitational field. By analyzing those arcs, their positions, their shapes, the degree of distortion, the way they curve around the cluster's center, astronomers can reconstruct the full mass distribution of the cluster, including the dark matter that contributes most of the lensing mass but is itself invisible. But lensing does more than map mass. It also provides a natural telescope for observing extremely distant objects. The magnification effect of gravitational lensing can amplify the light of background galaxies by factors of 10, 20, or even more, effectively making them appear as bright as if we had a telescope many times larger than Webb. Some of the most distant and intrinsically faint galaxies detected by Webb were only detectable because a foreground galaxy cluster was magnifying them, boosting their brightness enough to bring them within Webb's reach. This is a profound fact about the universe. Its own structure, the clusters and filaments and concentrations of dark matter that form the cosmic web, serves as an amplifier for our observations of its earliest history. Several of the most extreme early universe galaxies detected by Webb, the ones that have challenged formation models with their unexpectedly high masses, were found behind lensing clusters. Their detection was made possible by the magnification effect of the intervening mass. As researchers refine their understanding of the lensing geometry and the amplification factors involved, they are also refining their estimates of the true luminosities and masses of those background objects. In some cases, those revised estimates reduce the tension with standard models somewhat, without eliminating it entirely. At the center of the Milky Way, and at the center of virtually every large galaxy astronomers have studied, sits a supermassive black hole. The Milky Way's central black hole, designated Sagittarius A*, has a mass approximately 4 million times that of the Sun. Its existence was confirmed with extraordinary precision by two independent research groups. The teams led by Reinhard Genzel and Andrea Ghez spent decades tracking the orbits of stars in the dense stellar cluster surrounding the galactic center, and showed that those orbits were consistent only with the presence of an enormously massive compact dark object. This work earned Genzel and Ghez a share of the 2020 Nobel Prize in Physics. In 2022, the Event Horizon Telescope, a global network of radio telescopes operating as a single Earth-sized interferometer, released the first direct image of Sagittarius A*, a glowing ring of hot gas surrounding the dark shadow of the black hole itself. Supermassive black holes are not curiosities. They play an active and essential role in shaping their host galaxies. When a supermassive black hole is actively accreting material, drawing in gas and dust from its surroundings, the energy released by that accretion process can exceed the combined luminosity of all the stars in the galaxy. This phase of active accretion produces a quasar, one of the brightest persistent sources of light in the universe. The jets and radiation from an actively accreting black hole can heat or expel the gas in the surrounding galaxy, quenching star formation and fundamentally altering the galaxy's future evolution. Without black hole feedback, simulations of galaxy formation produce too many large actively star-forming galaxies compared to what observations show. Incorporating black hole feedback, in which the energy from accretion processes regulates star formation by heating and expelling gas, brings simulated galaxy populations into much better agreement with observed ones. Some of the most surprising discoveries from Webb's early operations involve the detection of actively accreting supermassive black holes in galaxies at extreme redshifts. These are black holes that were already extremely massive, millions or even billions of solar masses, when the universe was less than 1 billion years old. Building a black hole to those masses in that time requires either starting with an unusually large seed black hole and accreting at the maximum theoretical rate for essentially the entire available time, or accreting at rates that exceed what standard models permit. The existence of these massive early black holes is related to, and in some ways even more challenging than, the problem of the massive early galaxies. If galaxies formed unexpectedly early and grew unexpectedly fast, the same appears to be true of the supermassive black holes at their centers. The two problems may be connected. By contrast, Sagittarius A*, the Milky Way's own central black hole, is by cosmic standards remarkably quiet. It is currently accreting at a tiny fraction of its theoretical maximum rate. The Milky Way is not a quasar. It does not produce powerful jets of relativistic material. It is a dormant system, a galaxy whose most intense black hole activity, if it ever had such a period, lies far in the past. Our galaxy's central engine is essentially switched off. This is another way in which the Milky Way is unremarkable. A quiet, stable, middle-aged spiral galaxy in a state of steady, moderate star formation with a central black hole that mostly sits inert, occasionally accreting small amounts of material and producing brief, modest flares that instruments can detect but that are inconsequential by the standards of what active galactic nuclei elsewhere in the universe routinely do. Our galaxy is unremarkable. Our galaxy is ordinary. And that ordinariness, understood in the full context of what Webb has revealed about the universe, becomes in its own way remarkable. Because ordinary in a universe of 2 trillion galaxies means being one specific configuration of matter and energy and gravity among an effectively uncountable number of alternatives, each one governed by the same physics, each one following the same broad evolutionary path, each one unique in its specific details of history and composition and structure. The Milky Way is one of 2 trillion. It is the one we are in. Let us trace, as precisely as the confirmed science allows, the actual dimensions of the observable universe and the structures within it, from our galaxy outward, layer by layer, scale by scale, until we reach the outermost boundary of what the universe has allowed us to see. The Milky Way, a barred spiral galaxy approximately 100,000 light-years in diameter, possibly extending to 120,000 light-years when the full extent of its outer disk is considered. Its central bar spans roughly 27,000 light-years. Its spiral arms, of which the exact number is debated with estimates ranging from 2 prominent arms to 4, extend from the bar's ends outward through the disk. Our solar system sits in a minor spiral arm called the Orion Arm, or Orion Spur, located approximately 26,000 light-years from the galactic center. We are neither at the center nor at the edge. We are in the middle suburbs of the galactic disk, unremarkably positioned. The Milky Way's total stellar mass is estimated at 50 to 60 billion solar masses. Its total mass, including dark matter, is much harder to measure and is estimated at somewhere between 700 billion and 2 trillion solar masses, depending on how far out the dark matter halo extends. The dark matter halo may extend 600,000 light-years or more from the galactic center, making the total dark matter structure of the Milky Way 6 times wider than its visible disk. The large and small Magellanic Clouds, the Milky Way's 2 largest satellite galaxies, orbit at distances of approximately 160,000 and 200,000 light-years respectively. They are visible to the naked eye from the southern hemisphere as detached patches of the Milky Way, and they are the nearest galaxies beyond our own. Webb has imaged both clouds in extraordinary detail, revealing their star-forming regions, their stellar populations, and the complex gravitational interactions between them and the Milky Way that are gradually pulling them in. Beyond the Magellanic Clouds, the local group extends to a total diameter of roughly 10 million light-years, a volume of space containing our galaxy, Andromeda, the Triangulum Galaxy, and several dozen smaller dwarf galaxies. The local group is gravitationally bound. Its members are not being carried apart by cosmic expansion, because local gravity is strong enough to overcome the expansion within this volume. Beyond the local group, we enter the Virgo supercluster, which spans approximately 110 million light-years. The Virgo cluster at its center contains more than 1,300 member galaxies. The local group is near the outer edge of the Virgo supercluster, peripheral, gravitationally influenced by the larger structure, but not deeply embedded in it. The Virgo supercluster is itself a lobe of Laniakea, the 520 million light-year supercluster within which we reside. Beyond Laniakea, the cosmic web continues. Adjacent superclusters include the Perseus-Pisces supercluster, the Coma supercluster, and the Shapley supercluster, among the most massive concentrations of matter in the observable universe, extending in all directions across hundreds of millions of light-years. The Sloan Great Wall, identified in galaxy surveys using the Sloan Digital Sky Survey, spans approximately 1.37 billion light-years, making it one of the largest known structures in the observable universe. The Hercules Corona Borealis Great Wall, detected in gamma-ray burst surveys, is estimated to be even larger, possibly spanning 10 billion light-years, which would make it the largest known structure of any kind. Its reality and precise extent are still subjects of scientific discussion, with some researchers questioning whether it represents a genuinely coherent structure or a statistical artifact of the survey methodology. But its detection points to the possibility that the largest scales of cosmic structure are not yet fully characterized, that our maps of the universe at the very largest scales remain incomplete. At those scales, the universe should, according to the cosmological principle, look homogeneous, the same in all directions, smooth and featureless when averaged over sufficiently large volumes. The cosmic web's filaments and voids and clusters should average out into a uniform distribution at scales above roughly 1 billion light-years. If structures genuinely exist at scales of 10 billion light-years, the scale of homogeneity is being pushed toward or beyond the boundary of what standard models predict. That is a question Webb and its successors will continue to probe with increasing precision. Now consider what we know with confidence, as of this moment in the development of observational cosmology, about the universe's actual size and our place within it. The observable universe spans 93 billion light-years. Our galaxy spans 100,000 light-years, approximately 1/160th% of that diameter, and an incomparably smaller fraction of the total volume. The observable universe contains approximately 2 trillion galaxies, each a self-contained system of stars and dark matter and gas, each with its own history of formation, evolution, and future. Our galaxy is one of those 2 trillion. It is neither the largest, nor the most luminous, nor the most massive, nor the most structurally complex. Some galaxies in the universe are genuinely enormous by any comparison. IC1101, an elliptical galaxy at the center of the Able 2029 galaxy cluster, spans approximately 6 million light-years, 60 times the diameter of the Milky Way. Its stellar mass is estimated at roughly 100 trillion solar masses. It contains an estimated 100 trillion stars. If our galaxy were represented by a grain of sand, IC1101 would be represented by a boulder. The Milky Way, placed inside IC1101, would be an almost invisible feature in one corner of the larger galaxy's vast stellar halo. Marlin 1, a giant low-surface brightness spiral galaxy, has a disk extending approximately 650,000 light-years from its center, more than 6 times the diameter of the Milky Way's visible disk. Its stars are so sparsely distributed that its surface brightness is far below what ordinary spiral galaxies show, making it difficult to detect and study, but its sheer physical extent is extraordinary. The Tadpole Galaxy, currently undergoing a merger with a smaller companion, trails a tidal tail of stars approximately 280,000 light-years long, nearly 3 times the full diameter of the Milky Way, generated by the gravitational disruption of the merger. These are not exotic exceptions. They are examples drawn from the range of galaxy sizes and structures that populate the universe, a range that the Milky Way occupies at the unremarkable middle. Our cluster, the local group, is itself modest by comparison to the richest galaxy clusters in the observable universe. The Coma cluster, approximately 320 million light-years from Earth, contains more than 1,000 confirmed member galaxies within a region roughly 20 million light-years across. The Perseus cluster contains hundreds of member galaxies embedded in a vast cloud of hot X-ray emitting gas. The most massive known galaxy clusters, the so-called relaxed clusters at the centers of dense superclusters, contain thousands of member galaxies and total masses of quadrillions of solar masses. The local group, by comparison, has perhaps 80 members, the vast majority of them dwarf galaxies of negligible mass and luminosity. If the Coma cluster is a city, the local group is a small village on its outskirts, unconnected to the metropolitan density and dynamism of the larger structure. Beyond our local neighborhood, the universe has structures that strain the limits of description. The Shapley supercluster, approximately 650 million light-years from Earth, is one of the most massive concentrations of matter in the observable universe, a region spanning roughly 650 million light-years that contains dozens of galaxy clusters and thousands of galaxies. Its gravitational influence extends far beyond its boundaries, pulling nearby superclusters, including to a small but measurable degree our own Laniakea, toward it at velocities of hundreds of kilometers per second. The total number of stars in the observable universe is estimated at approximately 1 to 2 sextillion. Written out, that number has 21 digits. There is no intuitive way to grasp it. There is no analogy that adequately captures its magnitude. It is simply a number of a size that human cognition was not built to hold, reported honestly as the best current estimate of a quantity that is real and finite, even if it exceeds our capacity for direct comprehension. The age of the observable universe is 13.787 billion years, with an uncertainty of approximately 20 million years, a precision that reflects the extraordinary quality of cosmological data accumulated over recent decades. The density of ordinary matter in the observable universe, the atoms that make up stars, planets, gas clouds, and everything we can directly detect, amounts to approximately 5% of the universe's total energy density. The remaining 95% is split between dark matter at approximately 27% and dark energy at approximately 68%. Both of these dominant components are understood only in terms of their gravitational effects. Their fundamental nature remains unknown. We live in a universe whose composition is 95% mysterious to us. That is not a failure of science. It is a frontier, a clearly delineated boundary between what we know and what we do not, marked with great precision by the very observations that defined it. We know with high confidence that dark matter and dark energy exist. We know how much of each there is. We know how they behave gravitationally. We do not yet know what they are made of, whether they are single entities or composites, whether they are static or dynamic, or whether our current descriptions of them will survive the next generation of observations intact. Now, with all of these measurements in place, consider the map that modern astronomy has assembled. Imagine the entire cosmos laid out as a three-dimensional structure of extraordinary complexity, spanning 46 billion light-years in every direction from where we stand. In this precise instant of cosmic time, the map would show the cosmic web in its full form, filaments of galaxy clusters stretching like threads across hundreds of millions of light-years, voids of near emptiness occupying the vast spaces between those filaments, volumes of space so large that if you placed our entire local group inside one of them, it would be invisible against the scale of its surroundings. A handful of galaxies lost in a bubble of near nothingness, hundreds of millions of light-years across. Zoom into that map. Reduce the scale by a factor of thousands and Laniakea appears, 520 million light-years across, containing 100,000 galaxies flowing like rivers toward the gravitational basin of the Great Attractor at its structural heart. Zoom in further. The Virgo supercluster resolves into its constituent groups and clusters. The Virgo cluster at its center, dense and rich, with more than 1,000 member galaxies, surrounded by the sparser outlying groups. One of those outlying groups, near the periphery of the Virgo supercluster, small and sparse against the broader structure, is the local group. Zoom in further still. The local group resolves into its members, Andromeda large and spiral, its disk tilted toward us at an angle that makes it appear slightly oval in our sky. And across the 2.537 million light-years of intergalactic space that separates them, the Milky Way, our galaxy, home. This is the confirmed map that modern astronomy has assembled, layer by layer, scale by scale, over more than a century of increasingly precise observation. Every level of it is supported by measurement and evidence. Webb has not invented this map. It has sharpened it, filled in missing details, extended it closer to the beginning of time than any previous instrument, and made the comparisons at every scale more vivid and more undeniable than they have ever been before. The human being looking at a Webb deep field image is approximately 2 meters tall. The image contains galaxies separated from the viewer by distances measured in billions of light years. The ratio between the viewer and the most distant visible galaxy in that image is approximately the same as the ratio between a single atom and the entire observable universe. That ratio is not a cause for despair. It is not a message about meaninglessness. It is simply a fact about the structure of physical reality, a fact that only became accessible to us very recently through the extraordinary effort of building instruments capable of seeing it. Here, at the end of the measurements and the comparisons and the confrontations with scale, something needs to be said that the numbers themselves do not say, something that sits alongside them and gives them their full meaning. The numbers describe the universe's size. They do not describe its significance. Size and significance are not the same thing. A library is not more important than the ideas in its books because it is large. A galaxy is not more important than the life within it because it contains more stars. The scale of the universe tells us something about the universe's physical extent. It does not by itself tell us anything about what matters within that extent. What Webb's observations keep returning to, beneath all the specific discoveries and the revised estimates and the challenged models, is something simpler and harder to quantify. The universe is extraordinary. Not just large, extraordinary in its structure, its history, its complexity, its capacity to produce from simple physical laws an arrangement of matter and energy as intricate and varied and surprising as 2 trillion galaxies, each containing billions of suns, organized into filaments and clusters and voids across scales that exceed easy comprehension and yet governed by equations that fit on a single page. The laws of physics that produced all of this, the same equations that describe the expansion of the universe, also describe the orbit of the moon. The same quantum mechanics that governs the fusion reactions in stellar cores also governs the chemistry of the molecules in your cells. The universe is not a collection of separate domains operating under different rules. It is one system operating under one set of laws at every scale from the subatomic to the cosmological. The galaxies in Webb's deep fields were made of the same stuff we are made of, the same quarks and leptons, the same forces, the same constants of nature. They formed by the same gravitational physics that holds our solar system together. They shine by the same nuclear physics that keeps our sun burning. They are, in the most literal sense, related to us. Consider what happened on a rocky planet, orbiting an ordinary star in the outer arm of a medium-sized spiral galaxy approximately 9 billion years after the Big Bang. Chemistry organized itself into replicating molecules. Replicating molecules evolved into cells. Cells evolved into multicellular organisms. Multicellular organisms evolved over hundreds of millions of years into creatures with nervous systems complex enough to build models of their environment. Some of those creatures, in the last eye blink of cosmic time, developed language, mathematics, writing, and scientific method. They built telescopes and launched them into space. They aimed those telescopes at the darkest parts of the sky and found them full of ancient light. They read that light and reconstructed the history of the universe from its beginning to the present moment. The universe has been doing this for 13.8 billion years without anyone watching. Stars have been forming and dying. Galaxies have been colliding and merging. Black holes have been growing. The cosmic web has been assembling its vast architecture of matter and void, all of it, for nearly all of cosmic time, in the absence of anything that could observe it or record it or wonder about it. Then, very recently, in the last fraction of a percent of cosmic time, something arose that could, something small enough to be invisible on a map of the cosmos, temporary enough to register as a rounding error in the universe's age, but complex enough to build mirrors and point them at the dark and ask how large this is, and how old, and what does it mean? Webb's infrared mirrors, floating silently in space at temperatures colder than anything in the solar system, are collecting light from the earliest chapters of cosmic history and transmitting it as data back to the planet where the mirrors were designed and shaped and coded and assembled and launched. The universe is looking at itself through instruments that its own physical laws made possible. Instruments built from atoms forged in stellar interiors powered by a star whose formation was enabled by the structure of the galaxy that preceded it, operated by beings whose existence traces back through an unbroken chain of causes to the first moments of cosmic time. We are not observers standing outside the universe and studying it from a distance. We are the universe observing itself. The carbon in your body was forged in the interior of a star that died billions of years before the sun existed. The calcium in your bones came from a supernova. The iron in your blood traces its origin to stellar nucleosynthesis in the cores of massive stars that exhausted their fuel and collapsed. You are, in the most literal and material sense, made of the universe's history, and you, this configuration of stellar remnants organized by evolution into a pattern complex enough to sustain consciousness, are reading a map of where those remnants came from. The gold in Webb's mirror coatings was formed in the collision of neutron stars billions of years ago, scattered through space to eventually become part of the solar system, part of Earth, part of the materials that engineers shaped into the most precise astronomical mirrors ever fabricated. The universe is photographing itself through instruments made from its own substance. The journey Webb has started is not finished. Every new observational season produces findings that sharpen the picture and raise new questions. The earliest galaxies will be studied in greater detail, with better constraints on their masses and star formation histories. The Hubble tension will either be resolved by further precision measurements or will demand a deeper revision of the standard model. The dark matter distribution in galaxies and clusters will be mapped with greater fidelity through improved gravitational lensing analyses. The properties of dark energy will be probed through increasingly precise measurements of the expansion history. The timeline of cosmic reionization, the epoch when the first star's ultraviolet light ionized the neutral hydrogen gas that filled the early universe and made it opaque to most wavelengths of light, will be mapped in finer detail. The zone of avoidance, the band of sky blocked by our galaxy's disk, will become more transparent as infrared and radio surveys improve. Every answer Webb provides opens questions that were not previously visible. That is not a failure. That is the signature of science operating at the frontier, the boundary where what is known meets what is not, where measurements have outpaced theories and theories are reaching for new measurements. The boundary is moving. It has been in the solar system and observed a small fraction of the observable universe, and we built a telescope and aimed it at the dark. Begin with one image. A single photograph taken by James Webb, a patch of sky small enough to cover with a grain of sand, held at arm's length from your face. Inside that image, thousands of galaxies, each one containing hundreds of billions of stars. Each one, a complete independent island of light, built over billions of years by gravity and gas and time. Each one the context within which, if the numbers suggest what they seem to suggest, other configurations of matter are arising and looking outward, and asking their own versions of the question we are asking here. Look at that image long enough, and something shifts. The numbers stop being numbers and start being something closer to a felt reality. Not fear exactly, not awe exactly, something that sits in the space between those two words and has no precise name in any language. Something that arises specifically from the collision between the scale of what you are looking at and the scale of the thing that is looking. This is what Webb has given us. Not just data, not just revised estimates of galaxy counts or refined measurements of the Hubble constant, or tightened constraints on cosmological parameters. Though it has given us all of those things and they are valuable beyond easy calculation, it has given us a new felt sense of scale, of where we are, of how old the universe was before our galaxy existed, of how small our local neighborhood is inside the structures that contain it, of how much of what exists is already beyond our reach and receding further every second, of how extraordinary it is that we can measure any of this at all. The observable universe is 93 billion light-years across. Our galaxy is 100,000 light-years across. We live 26,000 light-years from its center. Our civilization is a few thousand years old. Our best telescope sees 13.8 billion years into the past and finds that the universe was already building galaxies before our planet existed. At every level of the map, we are a minor entry. We are accurately sized. And we built the map. That is not a small thing. That may be, in a universe of 2 trillion galaxies and 1 to 2 sextillion stars, the most remarkable thing we know of. Not the largest thing, not the oldest thing, not the most massive or the most luminous or the most energetic thing, but the thing that looked at all of those other things and asked what they were. If you found this video worth your time, consider subscribing. There is more science here, more questions Webb is still working to answer, and more of the universe left to understand than any single video can contain. The universe is vast. We are small within it. We looked anyway. Webb is still looking. To fully appreciate what Webb has revealed, it helps to dwell longer on the individual discoveries and the chain of reasoning that connects them, because each finding builds on the last in ways that multiply their significance. Start with the question of how we actually know the universe is 93 billion light-years across, rather than some other figure. The measurement depends on several independent lines of evidence that, remarkably, agree with each other to high precision. The first comes from the cosmic microwave background, the faint glow of thermal radiation that permeates all of space and represents the afterglow of the Big Bang itself. In the early universe, matter and radiation were so hot and dense that they formed a single tightly coupled plasma. Photons, the particles of light, could not travel freely. They were constantly scattered by the dense fog of charged particles that filled all of space. The universe was opaque. Then, approximately 380,000 years after the Big Bang, the universe had expanded and cooled enough that electrons and protons could combine into neutral hydrogen atoms. The fog cleared almost instantaneously in cosmic terms, and for the first time, photons were able to travel freely across space. The light that was released at that moment has been traveling ever since, and we can detect it today as the cosmic microwave background. It fills the entire sky uniformly, arriving from every direction simultaneously, a relic of that ancient moment of cosmic transparency. The Planck satellite, operated by the European Space Agency, mapped the cosmic microwave background with extraordinary precision between 2009 and 2013. The map revealed tiny temperature fluctuations in the background radiation, parts per 100,000 variations in temperature across the sky, that represent the primordial density fluctuations that would later grow into galaxies and the cosmic web. By analyzing the pattern of those fluctuations in exquisite detail, cosmologists could extract a wealth of information about the universe's geometry, composition, age, and expansion history. It is from this analysis that the figure of 13.787 billion years for the age of the universe comes, and from this analysis that the measurement of the universe's spatial flatness comes as well. The second line of evidence comes from the distribution of galaxies across large scales. By mapping the positions of millions of galaxies and measuring their distances using spectroscopic redshifts, astronomers can trace the three-dimensional structure of the universe over volumes spanning billions of light years. The pattern in that distribution, particularly a feature called baryon acoustic oscillations, a preferred scale of clustering that was imprinted in the early universe by sound waves propagating through the primordial plasma, provides an independent standard ruler for measuring cosmic distances. Measuring the apparent size of the baryon acoustic oscillation feature at different distances across cosmic history constrains both the expansion rate and the geometry of space. The third line of evidence comes from type Ia supernovae, those standardizable stellar explosions that were used in 1998 to discover the acceleration of the universe's expansion. By measuring the apparent brightness and redshifts of thousands of type Ia supernovae across a range of cosmic distances, astronomers can reconstruct the expansion history of the universe, mapping how the rate of expansion has changed over time. The agreement between these three independent methods in their fundamental constraints on the universe's age, geometry, and composition is one of the most impressive achievements in the history of science. It gives us the figures we have been working with throughout this video with justified confidence. Webb's contribution to this picture has been to refine the measurements at both ends of cosmic history. In the early universe, Webb's observations of high redshift galaxies add precision to our understanding of how structure assembled in the first billion years. In the more recent universe, Webb's measurements of Cepheid variables and other distance indicators sharpen the calibration of the cosmic distance ladder. Both ends of the timeline are becoming more precise, and the tension between them, the Hubble tension, is consequently becoming more clearly defined rather than fading away with better data. This is what makes the Hubble tension so scientifically interesting and so potentially important. It is not a case of imprecise measurements giving inconsistent results. It is a case of increasingly precise measurements giving consistently inconsistent results. The measurement of the Hubble constant from the cosmic microwave background says the universe is expanding at approximately 67.4 kilometers per second per megaparsec. The measurement from the distance ladder says approximately 73. Both numbers have error bars that have been shrinking as the measurements have been refined. And those shrinking error bars are not overlapping. They are moving apart. The gap, measured in units of statistical significance, has been growing rather than closing. In cosmology, the statistical threshold that commands serious attention is typically 5 sigma, meaning a result unlikely to occur by chance more than once in about 3.5 million trials. The Hubble tension has crossed that threshold by some analyses. It is not a statistical fluctuation that will vanish with more data. It is a systematic discrepancy between two well-characterized measurement methods applied to the same universe. Something is either wrong with one of the methods in a way that has not yet been identified, or there is a genuine gap in the standard cosmological model that the tension is revealing. What could that gap be? Physicists have proposed dozens of possibilities. Some involve modifications to the physics of the early universe, before the moment when the cosmic microwave background was released. Early dark energy is one such proposal. In this scenario, there was a brief period in the early universe when a component of energy with unusual properties was significant, contributing to the universe's energy budget in a way that altered the sound horizon in the primordial plasma and therefore shifted the baryon acoustic oscillation scale. If the sound horizon was smaller than the standard model predicts, the microwave background measurements would infer a higher expansion rate, reducing or eliminating the tension with the distance ladder. The challenge is that early dark energy models tend to create other tensions elsewhere in the data, and no single proposal has been convincingly shown to resolve the problem without creating new ones. Other proposals involve modifications to the physics of the late universe after the microwave background was released. These include dynamic dark energy models in which dark energy evolves over time rather than remaining constant, interacting dark matter models in which dark matter is not completely inert but exchanges energy with other components, and various modifications to general relativity at cosmological scales. Some theorists have explored whether the tension might be related to the local matter distribution, specifically whether we happen to live in a region of the universe that is slightly underdense compared to the cosmic average, which would cause local measurements of the expansion rate to be slightly higher than the global average. None of these proposals has yet emerged as the clear winner. Webb's data is one of the primary inputs in forming the ongoing comparison of these alternatives against observation. Its precision in measuring Cepheid variables, its contributions to refining the distance ladder, its deep observations that constrain models of early galaxy formation and constrain dark energy through large-scale structure measurements, all of these are inputs into the models being tested against the tension. The resolution of the Hubble tension, when it comes, will be one of the most significant advances in cosmology in decades. If the tension resolves through the identification of a systematic error in one measurement method, that will be important and instructive. If it resolves through the discovery of new physics, a modification to the standard model that accommodates both measurements consistently, that will be potentially transformative, the kind of revision that occasionally reshapes our understanding of the universe at a fundamental level. Webb is also reshaping our understanding of how galaxies like our own form and evolve. The detailed infrared observations it has made of nearby galaxies provide context for interpreting the more distant, smaller, less resolved images of galaxies across cosmic time. By studying the resolved stellar populations of nearby galaxies, the individual stars in different regions of the galaxy disk and halo and bulge, Webb can directly measure things that in more distant galaxies must be inferred statistically from the combined light of billions of unresolved stars. One particularly striking contribution from Webb's observations of nearby galaxies concerns star-forming regions. In the Milky Way and our neighboring galaxies, the regions where new stars are being born are embedded in dense clouds of gas and dust. Those clouds absorb the visible light from the young stars forming within them, making those stellar nurseries largely invisible at optical wavelengths. Infrared light penetrates the dust clouds. Webb's infrared instruments can see directly into these stellar nurseries, resolving the young stellar objects embedded within them, mapping the structure of the gas and dust at scales relevant to the formation of individual stars and planetary systems. Webb has imaged the Tarantula Nebula in the Large Magellanic Cloud, one of the most active star-forming regions in our local galactic neighborhood, with a detail that reveals an almost fractal complexity of structure. Filaments of hot gas, bubbles blown by stellar winds and supernova explosions, dense globules where new stars are contracting, clusters of newly formed massive stars, whose ultraviolet radiation and winds are beginning to reshape the surrounding material. The image is simultaneously beautiful and scientifically rich, illustrating the same processes of stellar birth that have been occurring in galaxies across the observable universe for billions of years. These detailed nearby observations matter because they provide the physical understanding needed to interpret the less resolved images of distant galaxies. When Webb observes a high redshift galaxy and measures its infrared brightness in different wavelength bands, the translation from those measurements to physical properties like stellar mass and star formation rate depends on models of how stars of different ages and types contribute to the infrared light. Those models are calibrated against observations of resolved stellar populations in nearby galaxies. Webb's detailed nearby observations therefore directly improve the accuracy of its distant universe science. There is another dimension to Webb's scientific program that deserves more attention than it typically receives in discussions of the telescope's discoveries: the search for the chemical fingerprints of the first generations of stars. The first stars that formed in the universe were made of almost exclusively hydrogen and helium, the two lightest elements, which were produced in the primordial nucleosynthesis of the first 3 minutes after the Big Bang. All of the heavier elements, carbon, nitrogen, oxygen, iron, calcium, and every other element beyond helium in the periodic table, were produced inside stars and dispersed into the interstellar medium by stellar winds and supernova explosions over the subsequent history of the universe. This means that the first stars, formed before any previous stellar generation, had had a chance to enrich the primordial gas with heavier elements, had a composition utterly unlike the Sun. Astronomers call these theoretical first-generation objects population 3 stars. They have never been directly observed. By the time they could be detected, they had already lived and died, because the most massive of them burned their fuel in millions of years rather than billions. But their existence is implied by the physics of the early universe, and their influence is encoded in the chemical abundances of subsequent stellar generations. Webb is searching for the signatures of population 3 stars in 2 ways. First, by looking at extremely high redshift galaxies in the early universe, where the first stellar generations may still have been active, and where the chemical composition of the galaxies may show the imprint of those first stars. Second, by studying the spectra of the oldest and most chemically primitive stars in nearby galaxies, including the Milky Way, which carry the chemical fingerprints of the stellar generations that preceded them. The chemical abundances in the oldest stars of the Milky Way's halo, the diffuse population of stars orbiting above and below the disk, tell a story about the kinds of stars that enrich the galaxy's gas in its earliest epoch. Some of these ancient stars are so chemically primitive that they have iron abundances thousands of times lower than the Sun, meaning they formed when the interstellar medium had been only lightly enriched by previous stellar generations. The pattern of element abundances in these ancient stars, the ratios of carbon to iron, of barium to strontium, of the various alpha elements like magnesium and silicon to iron, carries information about the masses and evolutionary histories of the stars that enrich the gas from which they formed. Webb's spectroscopic capabilities, particularly its ability to obtain high-quality spectra of faint objects at near-infrared wavelengths, make it an important tool for this kind of chemical archaeology. By studying the spectral signatures of gas in high-redshift galaxies, Webb can measure the abundances of multiple elements in the early universe and compare them against models of how those abundances should evolve as successive generations of stars live and die. The goal is to constrain the properties of the first stellar generation, whose existence we have never directly observed, by tracing its indirect influence on the chemistry of what came after. The merger history of the Milky Way is another area where Webb's observations contribute to a rapidly developing field. Our galaxy carries the archaeological record of its past interactions in the chemical compositions and kinematics of its stellar populations. Data from the Gaia space mission, which has mapped the positions and velocities of more than 1 billion stars in the Milky Way with extraordinary precision, has revealed the stellar streams and debris from ancient mergers, galaxies that fell into the Milky Way billions of years ago and were disrupted and absorbed, their stars now distributed through the halo in distinctive kinematic patterns. One such ancient merger, dubbed the Gaia Enceladus or Gaia Sausage event, appears to have been a major collision between the early Milky Way and a large companion galaxy approximately 8 to 11 billion years ago. The stars from that absorbed galaxy are identifiable today by their chemical signatures and orbital properties, a fossil population embedded in the Milky Way's halo, carrying the memory of a catastrophic event from before the solar system existed. The Milky Way we inhabit today is partly the product of that ancient collision. Our galaxy is not the pristine, isolated system it might appear to be. It has a violent past. Webb contributes to this research by observing the resolved stellar populations of nearby galaxies in the infrared, providing data that complements Gaia's Milky Way survey and extends similar analyses to our galactic neighbors. Understanding the merger histories of nearby galaxies provides context for interpreting the statistical evidence of mergers in more distant, unresolved systems, building a comprehensive picture of how galaxies assemble through the accumulation of smaller pieces over cosmic time. Galaxy mergers play a crucial role in the broader story of how the universe's structure evolved. The universe's galaxies are not static objects. They interact with their neighbors, fall together under mutual gravitational attraction, and merge into new configurations. These mergers are among the most energetic events in the universe's history, collisions involving billions of stars and stretching over hundreds of millions of years. During a major merger, the star formation rate in the merging systems can spike dramatically as gas clouds collide and compress, triggering the formation of new stars at rates far higher than in isolated galaxies. The collision also drives gas toward the central supermassive black holes of both galaxies, potentially triggering quasar activity and ultimately reshaping both merging systems into the elliptical galaxy that often results from the collision's completion. Webb observes mergers at multiple stages and multiple epochs. In the nearby universe, it images known merging pairs in exquisite detail, tracing the tidal tails of stars flung outward by gravitational interaction, the bridges of gas connecting the merging systems, and the signatures of enhanced star formation in the collision zones. In the distant universe, it identifies the early stages of mergers in protoclusters, dense concentrations of galaxies. In the early universe, where close gravitational encounters and eventual mergers were frequent and consequential, the era of peak galaxy merging activity coincided broadly with the era of peak cosmic star formation, when the universe was roughly 2 to 4 billion years old. Both activities have declined since then, as galaxies have consumed their gas supplies, as the mutual separation between galaxies has grown due to cosmic expansion, and as the large-scale environment has become less dynamically active. We live in what is, by cosmic standards, a quieter epoch. The dramatic events that shaped the structures we observe today mostly occurred billions of years before the solar system existed. Webb's ability to observe the universe at those earlier, more active epochs and compare what it finds against theoretical models has given cosmologists a powerful new probe of how the cycle of galaxy formation, star formation, black hole growth, and merger activity operated when it was at its peak. The results, consistently, are a universe that assembled its large-scale structures somewhat faster than the most successful models predicted, and that hosted more massive and more organized galaxies at earlier epochs than those models expected. Whether this reflects a gap in our theoretical understanding, observational uncertainties at extreme distances, or some combination of both, remains one of the most actively debated questions in modern astrophysics. What we can say with confidence is that Webb has not closed the book on any of these questions. It has opened new chapters in each of them. The telescope's observational program extends years into the future, with each cycle of observations building on the last, each new dataset adding constraints that distinguish between competing explanations. There are also questions that Webb will help answer that go beyond the specific topics discussed here. One concerns the ionization of the universe, the epoch when the neutral hydrogen gas that permeated the cosmos in the first few 100 million years after the Big Bang was ionized by the ultraviolet radiation from the first galaxies and quasars. Before ionization, the universe was opaque to ultraviolet light, and the hydrogen gas formed a fog that obscured sources of ultraviolet radiation from distant observations. After ionization, the fog lifted, and the universe became the transparent medium it is today. The timing and nature of ionization, how quickly it progressed, which sources drove it, and how it varied in different regions of the universe, are all questions that Webb's observations of high redshift galaxies and quasars are actively addressing. Another concerns the relationship between dark matter and the galaxies that form within it. The dark matter distribution in the universe is not smooth and uniform. It is structured, with denser regions that form halos within which visible galaxies and their gas reside, and less dense regions that correspond to the voids and underdensities between filaments. The properties of those dark matter halos, their masses, their concentrations, the way they merge over time, determine in large part what kinds of galaxies form within them and how those galaxies evolve. Webb's observations of galaxy populations across cosmic time, combined with gravitational lensing measurements that probe the dark matter distribution directly, are providing new tests of the relationship between dark matter halos and their galaxy contents across billions of years of cosmic history. A third concerns the epoch of the first light in the universe. Before the first stars ignited, the universe was dark. Not dark in the sense of empty, but dark in the sense that there were no luminous sources to illuminate it. The primordial hydrogen and helium gas cooled and slowly collapsed under gravity, forming the structures within which the first stars would eventually ignite. The moment the first stars turned on, the universe's dark age ended. That transition, from a universe without any luminous sources to a universe with the first stellar fires burning, is one of the most dramatic events in cosmic history, and it is one that no existing observation has yet directly captured. Webb is searching for the signatures of that transition, both in the spectra of the most distant galaxies and quasars it can detect, and in statistical signals of the earliest star formation encoded in the properties of those objects. Every one of these frontiers represents a scientific question of the first order, a question whose answer will substantially deepen our understanding of how the universe we inhabit came to be the way it is. Webb is the primary instrument humanity has currently deployed to address those questions, and its answers will shape the direction of cosmological research for decades. The universe that Webb is revealing is one where the scale of complexity matches the scale of physical extent. It is not just large, it is organized, structured, historically layered, and in continuous evolution. The 2 trillion galaxies in the observable universe are not a random collection of identical objects scattered uniformly through space. They are a diverse population of systems at different stages of evolution, different sizes and masses, different histories of merger and star formation and black hole activity, organized into a hierarchical structure of groups, clusters, superclusters, and filaments that reflects the specific pattern of density fluctuations present in the universe. At the moment of the Big Bang and amplified by gravity over 13.8 billion years, every galaxy in that census is unique. Everyone has a particular assembly history, a particular complement of stellar populations spanning different ages and chemical compositions, a particular dark matter halo with a particular density profile, a particular central black hole at a particular stage of its evolution. Our galaxy, the Milky Way, is one specific realization of this process, formed in a particular region of the cosmic web, assembled through a particular sequence of mergers and accretion events, enriched by particular stellar generations, currently in a particular state of moderate star formation with a dormant central black hole and 2 satellite dwarf galaxies in the process of being absorbed by its gravitational field. Understanding the Milky Way in this full context as one galaxy among 2 trillion, as one specific outcome of processes that have been running for nearly the age of the universe, as a system whose present state is the result of a history beginning with the primordial density fluctuations of the Big Bang and running through every merger and star formation event since, is the goal of a generation of astronomical research. Webb is one of the most powerful tools that generation has. What is perhaps most remarkable about Webb's program of observation is not any single finding, dramatic as some of those findings have been, but the cumulative effect of the picture it is assembling. Season by season, observation by observation, the universe that Webb is revealing is one where the scales of space and time that matter are almost incomprehensibly larger than the scales of everyday human experience, and yet the physics that operates across those scales is exactly the same physics we have identified and tested in laboratories on Earth. The same constants of nature, the same quantum mechanics, the same gravitational theory, the same nuclear physics, govern the fusion of hydrogen in a stellar core 13 billion light-years away, as govern the fusion of hydrogen in the Sun 8 minutes of light travel time away. The universe is coherent, its laws are universal, and the instruments we have built from the materials of that universe are capable of reading those laws across its full extent. That coherence is not obvious. It is not something that had to be true. One could imagine a universe where the physics changed at large scales, where the laws of nature were local rather than universal, where what we measured in a laboratory here gave no information about what operated in a galaxy 12 billion light-years away. The fact that the universe is not like that the same physics applies everywhere and at all times that we can probe, is a profound and deeply non-trivial fact about the structure of physical reality. It is a fact that Webb is confirming at the furthest observational reach ever achieved by a scientific instrument. When Webb detects a galaxy at a redshift of 13, meaning the universe has expanded by a factor of 14 since that light was emitted, and finds hydrogen emission at exactly the wavelength shifted by exactly the amount predicted by quantum mechanics and the measured expansion history, it is confirming that quantum mechanics, discovered in laboratories in the first half of the 20th century, operated correctly in a galaxy that existed when the universe was 300 million years old. When it detects the gravitational lensing of background galaxies by foreground clusters and finds the distortion pattern consistent with general relativity applied to the measured mass distribution, it is confirming that the theory of gravity developed by Einstein in 1915 applies correctly at distances of billions of light years. These are not small confirmations. They are deep verifications of the universality of physics, conducted at scales and epochs that were completely inaccessible to observation before Webb's launch. Science proceeds at the frontier, and the frontier is always the boundary between the known and the unknown. Webb has moved that boundary dramatically in one direction, the direction of early cosmic time and deep extragalactic space. It has revealed that the universe at those extremes is, in its broad physical character, continuous with the universe we observe nearby. The same kinds of galaxies exist, the same physical processes operate, the same hierarchical structure of matter distribution holds. But the details, the specific abundances of early galaxies, the masses of early black holes, the rate of early structural assembly, are providing new tests of the standard model that are creating productive tensions and demanding theoretical development. The resolution of those tensions, when it comes, will not diminish what we understand. It will add to it. It will add precision to a picture that is already detailed enough to be transformative compared to what any previous generation of astronomers could work with. The universe Webb is revealing is the same universe that earlier generations of astronomers studied with less powerful instruments. It is the same universe that Hubble glimpsed in his observations of Cepheid variables in distant galaxies a century ago. It is the same universe that Henrietta Swan Leavitt helped to measure when she identified the period-luminosity relationship in Cepheid variables. But the detail and the depth and the precision with which we can now see that universe, and the breadth of the questions we can now ask and begin to answer, have been transformed. Webb is still in its operational lifetime. Its cryogenic coolant, which keeps its instruments at the temperatures needed for optimal infrared sensitivity, was supplied with enough reserve from the launch trajectory to support operations for more than a decade beyond its original design lifetime. The telescope has years of operation ahead of it, years in which it will continue to refine the picture it has been assembling and reveal new aspects of the universe that current observations have not yet reached. Future observatories will extend what Webb has done. Planned and proposed missions include large aperture space observatories operating at optical and ultraviolet wavelengths, which will complement Webb's infrared strengths with capabilities in the wavelength ranges that Webb cannot access. Ground-based, extremely large telescopes with primary mirrors 30 to 40 meters across will combine the light collecting area needed for detailed spectroscopy of faint high redshift objects with the adaptive optic systems needed to correct for atmospheric blurring. These instruments will work together to address the questions that Webb is opening, pushing the frontier further in both spatial and temporal depth. The generation of astronomers who will use those instruments is being shaped right now, in part by the results that Webb is producing. The discoveries that have made headlines, the unexpectedly massive early galaxies, the unexpectedly large early black holes, the confirmation and sharpening of the Hubble tension, the deep field images that revised upward the galaxy count. These are the scientific results that are defining the questions that the next generation of observers and theorists will spend their careers addressing. Science is cumulative and iterative. Every generation builds on what the previous generation established, adds new observations, develops new theories, and identifies new questions that only the most precise measurements of the current epoch could have revealed. Webb sits at a particular moment in that process, the moment when instruments became sensitive enough to see the universe in its infancy, and detailed enough to compare what they see against theoretical predictions, with enough precision to identify where those predictions fall short. That moment matters. It is a moment of genuine scientific productivity, of the kind that advances not just knowledge of specific objects and events, but the underlying theoretical framework within which all of that specific knowledge is organized. The standard cosmological model that Webb is testing is the most successful quantitative model of the universe ever developed. Its successes are extraordinary in their scope and precision, and the tensions that Webb is finding, the early massive galaxies, the Hubble tension, the possibility of structure at scales larger than the cosmological principle strictly permits, are precisely the kind of productive challenges that, historically, have led to the deepest advances in theoretical understanding. We do not yet know exactly what those advances will be. We do not know whether the Hubble tension will resolve through better measurement of existing quantities or through the discovery of new physics. We do not know whether the early, massive galaxies will ultimately be explained by modifications to standard star formation models, or by modifications to the standard model's description of dark matter and structure growth. We do not know whether the largest scales of the cosmic web will prove consistent with the cosmological principle at the precision Webb and its successors can probe. What we know is that the questions are real, the measurements are improving, the theoretical work is active, and the instruments exist to continue pushing the boundary. That is the state of the science of the universe's size in the era of James Webb. Not concluded, not complete, not comfortably explained, but actively explored, precisely measured, and rich with questions that the answers themselves have revealed. The universe is 93 billion light-years across, contains 2 trillion galaxies, is 13.787 billion years old, and was producing coherent, organized structure within its first few hundred million years of existence. Webb has confirmed all of this and added precision to every element of the picture. In doing so, it has not diminished the universe's strangeness or reduced the depth of our ignorance at its frontier. It has made the picture sharper, the questions clearer, and the gap between what we know and what there is to know more precisely defined. That gap is where science lives. Webb has made it the most interesting gap in the history of observation. The scientists and instruments that follow will spend decades working to close it, and in closing it, will almost certainly reveal new gaps that could not have been seen without the precision that preceded them. This is the nature of genuine inquiry into the universe. It does not terminate in final answers. It produces better questions. Webb has given us better questions than any instrument before it. The universe that raises them is 93 billion light-years across and still largely unknown. We looked anyway. We keep looking. Let us close by walking back through the chain of scale one more time, slowly, because it is worth sitting with each level before moving to the next. You are on Earth. Earth is a rocky planet, about 12,700 kilometers in diameter, orbiting the Sun at a distance of roughly 149.6 million kilometers. The Sun is an ordinary yellow dwarf star, about 109 times Earth's diameter, powered by nuclear fusion in its core, converting approximately 600 million tons of hydrogen into helium every second. The Sun has been doing this for approximately 4.6 billion years and will continue for approximately another 5 billion before exhausting the hydrogen in its core and expanding into a red giant. The nearest star to the Sun is Proxima Centauri, 4.24 light-years away. If you scaled the solar system so that the distance from the Earth to the Sun was 1 centimeter, the distance from the Sun to Proxima Centauri would be just over 2.5 kilometers. The stars are not crowded together. Space between them is genuinely enormous, even at the scales where they feel most densely packed. The Milky Way contains somewhere between 200 billion and 400 billion stars, distributed across a disk approximately 100,000 light-years in diameter and about 1,000 light-years thick in most places, thickening toward the central bulge. Our solar system sits 26,000 light-years from the galactic center in the Orion Arm, a minor spiral feature between two of the galaxy's more prominent spiral arms. Light takes 26,000 years to travel from the galactic center to us. The center of our own galaxy is as remote from us in time as it is in distance. The light we receive from the galactic core tonight left it 26,000 years ago, before the development of writing, before the construction of any permanent human settlement, before the extinction of the last mammoths. From the center of the Milky Way to its edge, is another approximately 24,000 light-years. Beyond the visible edge of the disk, the galaxy continues in the form of its dark matter halo, which extends perhaps 600,000 light-years from the center, a vast invisible structure that is in terms of total mass the dominant component of the galaxy. The disk of stars we can see, the thing we call the Milky Way when we look up at the night sky, is a luminous thin film on the surface of a much larger dark mass. Beyond the Milky Way's dark matter halo, 2.5 million light-years away, is Andromeda. Beyond Andromeda, the other members of the local group are scattered across a volume roughly 10 million light-years across. Beyond the local group, the Virgo supercluster spans 110 million light-years. Beyond the Virgo supercluster, Laniakea spans 520 million light-years. Beyond Laniakea, the cosmic web of filaments and voids extends to the edge of the observable universe at 46.5 billion light-years. At every transition in that chain, the scale increases by a factor that feels incomprehensible in the context of the previous level. The distance to Proxima Centauri is about 270,000 times the distance from Earth to the Sun. The diameter of the Milky Way is about 24 billion times the distance from Earth to the Sun. The diameter of the local group is about 100 times the diameter of the Milky Way. The diameter of the Virgo supercluster is about 1,100 times the diameter of the Milky Way. The diameter of the observable universe is roughly 930,000 times the diameter of the Milky Way. Each of those multiplications represents a genuine jump in the scale of structure, a genuine increase in the scope of what you are imagining when you hold the image in your mind. And yet the physics at every level is the same. The quantum mechanics that governs the nuclear reactions in a stellar core also governs the chemistry of the molecules in the primordial gas cloud, from which that star formed, and the gas cloud that will eventually collapse to form the next generation. The gravitational physics that determines the orbit of Earth around the Sun also determines the orbit of the Milky Way within the local group and the motion of the local group within the Virgo supercluster and the flow of Laniakea toward the great attractor. One set of laws, every scale, every epoch, the same. This is what makes the universe scientifically intelligible at all. If the physics changed at large scales, if the quantum mechanics that works in a laboratory somehow failed or transformed into something different at galactic distances, if gravity operated differently at cosmological scales than at stellar scales, then the program of using physics to understand the universe would be fundamentally compromised. The fact that we can measure the speed of light in a laboratory on Earth and use that measurement to interpret the redshifts of galaxies billions of light years away, that we can measure the nuclear physics of hydrogen fusion in our Sun and use those measurements to model the luminosity of stars in the earliest galaxies, that we can observe the gravitational lensing of distant galaxies and find it exactly consistent with the general relativity developed to describe the motion of planets in our solar system, is a fact of extraordinary significance. The universe is not just vast, it is coherent. Its vast scale is not a barrier to understanding it. It is, through the universality of physical law and the sufficiency of the speed of light to carry information across those vast scales to instruments we have built and aimed carefully, exactly the structure within which understanding becomes possible. Webb's $17 billion price tag, enormous as it sounds in human economic terms, is negligible against the universe it is being used to study. The total cost of designing, building, testing, launching, and operating the telescope represents a vanishingly small fraction of humanity's annual economic activity. What it has returned in scientific understanding, in revised estimates of galaxy populations, in refined cosmological parameters, in new constraints on models of early galaxy formation, in measurements relevant to the Hubble tension, in images of gravitational lensing arcs and high redshift galaxy clusters, and the star-forming regions of nearby galaxies, is incommensurable with economic value in any conventional sense. It is scientific knowledge of the kind that changes how a species understands its place in physical reality. That is not a category that has a market price. What Webb has given us is a more accurate account of where we are, not where we want to be, not where a pre-scientific intuition suggests we should be. Where we actually are, measured as precisely as the technology permits, placed in a context as complete as our observational reach allows. The picture that emerges from that measurement and that context is one of extraordinary scale and extraordinary coherence. of a universe that has been building structure for 13.8 billion years by the operation of physics we can measure and describe, of a small planet orbiting an ordinary star in an unremarkable galaxy where, in the last tiny fraction of cosmic time, something arose that could look outward across billions of light years and begin to reconstruct the history of all of it. That something is us. That reconstruction is science. Webb is its sharpest current instrument. The universe is vast. We are small within it. We looked anyway, and in looking, we did something the universe had not done, anywhere we know of, for billions of years before we existed. We understood. If you found this exploration of the universe's true scale worth your time, consider subscribing for more science content like this. There is much more to explore, and the questions Webb keeps raising are among the most extraordinary that any generation of humans has ever had the tools to seriously ask.